Alright, well, I almost certainly could have fit the last problem in the previous video, but I've learned to be a little leery of making the videos too long and having troubles kind of uploading them. So the last problem here, right, takes a little different approach, so worth maybe taking a little more time to discuss it. So we've got a salt, and we don't know what its composition is. We've determined that it's either sodium fluoride, sodium chloride, or sodium hypochlorite. But we have a pH meter, so we take a sample of the salt, we weigh it out, we know how many moles that is, we dissolve it in a certain quantity of solution to get up to half a liter, and we measure the pH. And from the pH, we want to figure out what the identity of that particular salt is. So what we know here is that the salt contains an ion, fluoride ion, chloride ion, or hypochlorite ion. Now, I'd say right off the bat we can eliminate one of these possibilities, because the sodium ion and the chloride ion in NaCl, neither of those should have any effect on the pH, because chloride is the conjugate of HCl, which is a strong acid, and sodium is conjugate of sodium hydroxide, which is a strong base. So we can just eliminate that sodium chloride because that pH should be 7, right? And HCl, very large Ka, is another way of saying, yeah, the reaction just goes forward because HCl is a strong acid. Now, the other two are both possibilities, so those are both weak acids. There's a fair difference in their Kas here, but what we want to figure out is how can we identify what is happening in this solution. So if we think about one thing going on here is we're given Kas, but what's happening in the solution here is we just have the base. So if we just have the weak base in solution, I'm going to use A- because this could apply to either of our two possibilities. And this is the reaction that we're looking at. Weak acid is going to form, and then we're going to get some hydroxide ion. Now, if we can calculate what the concentration of hydroxide ion would be for either of these solutions, we can figure out what the pH would be in that particular case. And since we have enough information to figure out the concentration, that's maybe a good way to approach this problem. We can take our concentration, plug in, solve for the pH, see if it matches 8.08. The other way you could approach the problem is you could take that pH, work backwards to hydronium ion concentration, use that to solve for concentrations at equilibrium, and calculate the Ka and compare that to what you see there. But I've already kind of decided that the good way to do it would be to solve for the pH. So let's go through and do it that way. But there is another way you could approach this problem. So we need concentration of our weak base if we're going to do that. So A- concentration is going to be 0.05 moles. That's how many we've got, divided by a half a liter, 0.5 liters. So the concentration here is 0.1. 0.1 molar, right? Although 2 sig figs, so keep that in mind. So I ran a little into my ice chart there, but initially, if our concentration is 0.1, no products yet under initial conditions, we know we've got minus x here, plus x here and here. By equilibrium, this is 0.1 minus x, and x. Now, once we get those, right, one thing we'd want to do is see if we can ignore the minus x, right? The other thing we would want to do then is plug into our expression. Now, this is not an acid reaction, this is a base reaction. So if we take our Kas here, we need to figure out what Kb is in order to even approach whether the assumption makes sense. So the first one listed is HF here. Let's use that one first to see if that's maybe our candidate. So Kb is going to be equal to Kw divided by Ka, since Ka times Kb equals Kw. So if I take 1 times 10 to the minus 14th and divide by the provided Ka here, that will give me Kb for fluoride ion. So 1 times 10 to the minus 14th divided by 7.2 times 10 to the negative 4, and I get 1.39 times 10 to the minus 11th for KB. Now, in terms of our assumption here, how is this minus x going to relate to 0.1? Right, my concentration is 0.1, and my constant is times 10 to the minus 11th. I've got 10 orders of magnitude difference here, so 10 billion or so. So the assumption would be just fine if we're talking about HF. So if that is the case, right, I can take my KB and I ignore the minus x. The equilibrium constant expression is going to be products over reactants. Both of the products are x, right, and the reactant is 0.1. I can solve for x here and see that'll be hydroxide ion. See if that matches the pH of this solution. So if I take 1.39 times 10 to the minus 11th, multiply it through by 0.1, and then take the square root of both sides, I get x equal to 1.18 times 10 to the minus 6th. That would be my hydroxide ion concentration. From there, I can get POH by taking the negative log. So negative log of my previous answer is 5.93. Right? If I subtract that from 14, I get a pH of 8.07. Right? Now that's not quite 8.08, but I think that's close enough to recognize that this is the correct identity of my compound, that it is sodium fluoride. Now, if we did the hypochlorous acid, right, you could do the same thing, just use this Ka to calculate the correct Kb. You could work through and figure out what the pH would be there, but since we've already identified that it's sodium fluoride, we really don't need to do that. But again, there's another way to kind of think about approaching this problem, is that you could use this pH. If you use this pH, you could figure out what the hydronium ion concentration is at equilibrium, use that to figure out the hydroxide ion concentration at equilibrium, and then you could solve the ice chart because you'd have this value. You'd know what the changes were. You could figure out all the concentrations at equilibrium. Once you've got all three of those concentrations, you plug into your equilibrium constant expression, and you could calculate Kb, use that to calculate Ka, and compare. So I think this is maybe a little more straightforward, but that's important to recognize there are other ways you could go about solving that problem.